Oui, parfait.
Okay.
Please wait 2 minutes because, yeah, a lot of people have not yet joined.
Okay.
That you can go.
Okay.
Yeah.
So I was going to say, so there are a new behaviors of qubits compared to classical bits, and these new characteristics make the quantum computing very interesting. And those characteristics are superposition, the fact that the qubit can be uh, either in zero or in one state, but also in a superposition of those two states. So it can be in a linear combination of these two states, and that makes things much more interesting than the classical counterpart. There are also this entanglement characteristic, which is really yes. Someone speaking now? No. Okay. This entanglement, which is very specific to quantum mechanics and which is very strange, which is the this 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 thing that two quantum mechanical systems which have interacted in their history in the past can still share a correlation together, and somehow the information stored in those two systems is delocalized in those two systems, and that you cannot consider the two systems isolated, but they form a full system together, and you have to take into account the full system in order to retrieve all the information. There is also the measurement problems in quantum mechanics, which is very new compared to what we see in the classical physics world. Measurement wasn't really an issue in classical physics. When we measure the velocity of a particle and the position of a particle, there is no big questioning about what are those characteristics of the physical object we are looking for. In quantum mechanics, those questions are very crucial, and you cannot ask all the questions at the same time and get an answer, a full answer to your questions. And you can only speak about probabilities to get a certain answer to your questions. So especially if you ask, for example, what is the position of this electron, you are only able to give probabilities for certain positions. And there is another characteristic, which is decoherence, which is very critical for building quantum computers, which is the characteristic of those quantum objects to interact with their environment and to somehow lose their quantum state. So if we lose, well, they don't lose their quantum state, but we lose information about the quantum state. So we know that those systems will interact somehow with their environment, and the state we thought the system was in after a certain amount of time will change, and we don't know how it will change. And this time, the time before this process happens is called the decoherence time. And when we use some technology to build the qubits, we have to look for technology, technology which have a good decoherence time. That means that they don't interact too much with their environment. Uh, Here is a presentation of several types of quantum computers. So there are different computers that can be built, quantum computers. There are computers that we call the quantum annealers, which are um, computers that you can think like a watch is designed to give the time. Always it does the same things. It gives the time. So a quantum annealer also is geared like that. So it's built to do a certain action, and it will do the same action every time. Uh, for instance, those quantum annealers are good to find a minimum of functions. So if you're able to somehow design your problem as the finding of the minimum of a function, you can use a quantum annealer to solve your problem. So it's a matter of trying to translate your problem into the language of the quantum annealer, which is finding the minimum of a function. Uh, on the right, the most right, you have quantum simulators, which are like quantum annealers. They they are special arrangements of quantum mechanical objects, which can mimic the behavior of a material, for example, and you can simulate the behavior of and simulate and compute properties of these materials with the help of these simulators. And in the middle, you have what we call the universal quantum computers based on quantum gates, which are the analogs of classical logical gates that we use in our CPUs, etc., with transistors and things like that. And in principle, you can address all kind of problems with this kind of quantum gate-based computers. Just a few words about building a quantum computer. So the building block of a quantum computer is the qubit. So when you want to build a quantum computer, you have to choose a qubit technology. Qubit technology, there are several of them, and all presents some advantages and some disadvantages. And when you choose one, you have to keep uh, to keep look of a certain criteria. Um, for example, you have to choose a quantum technology where the qubits can keep their quantum character for a long time. So that was I was talking about with decoherence. If they have a long decoherence time, so you know that those quantum bits will keep the quantum states for a long time. Uh, so that means that those qubits will not interact too much with their environment. But at the same time, you have also to manipulate those qubits in order to put some to make some computation. So you have to make some actions on those qubits, and you have to manipulate them to apply gates, and that means that you have to interact. So that we have something like a paradox of two things which are going in two opposite directions. You have to isolate the qubits, but at the same time make easy of the manipulation of these qubits. And also you have to the measurement of the final states of those qubits should be easy to do. So that's all kind of criteria you have to take into account when you want to build a quantum computer. Here is a table with different technologies and the advantages and maybe sometimes the disadvantages of the different ones. And so you see for realizing qubits, there are different technologies used: superconducting technology, trapped ions, photons are quite fashion at the moment, neutral atoms also. All are present. Some of them you see the coherence time. Some of them have no coherence time because these characteristics don't really apply to photons, for example, don't interact too much with the environment. So it's just a table to give you some technology. It's not exhaustive, but some technologies used to build qubits. Um, so I told you when I presented the different era of quantum computing, the challenges of scalability. So up to now, we're able to put a couple of hundreds of qubits together to work together. It's not really enough to do interesting things yet, but people are working hard to try to scale up. Uh, when you talk about the scalability challenge, you have to face also another problem, which is the connectivity problem. I mean that when we build a quantum computer, what is interesting in quantum computing is to make the qubits interact together, and especially to put some entanglement between different qubits in order to do interesting things. Uh, that's when we think theoretically, so there is no problem. I say, well, I entangle qubit 1 with qubit 10, that's it. But physically, those qubits are realized on something physical, and they they don't they can't interact together directly. So you have this um, in order to make qubits interact with another qubit, maybe you have to make it interact through other qubits in order to reach another qubit. So you have this connectivity. That's the diagram we see here. I don't know if you see my mouse. Yes, okay. That's this diagram, this connectivity diagram you see here. And so the machine you see here is the IBM machine, the machine built in 2019. And inside it looks like that. Why it takes this funny shape is because you have to isolate from the vibrations, isolate from the electromagnetic fields, and you have to have very low temperatures. So you have you cool down the system, and with the computation is done at the bottom here, where you are very close to the 0 Kelvin temperature. Uh, well, I talk about little bit about error corrections. Error corrections uh, uh, is something we try to so we try to fight the errors induced by the environment, and there are ways to do that. And the strategy basically is to replicate somehow the information on 1 qubit to several qubits. And this technique consumes physical qubits. And so in order to build a useful qubit, we consume a couple of physical qubits to do that. So we have this notion of logical qubit that is the aggregate of several physical qubits. And the last point is the space and the cost of those quantum computers. Quantum computers are big machines, so there are some pictures here. This is the D-Wave machine, and so and you have to isolate them. For example, here, so you have to have somewhere to put this machine and to isolate it perfectly, etc., etc. And they cost a lot of money to do things which are really not impressive at the moment. But it's necessary, I mean, to develop those prototypes in order to prove that we can have in the near future something interesting. Yeah, some big names involved in the field. So you find all the most important names: Google, IBM, etc. Some French companies also are involved in the field. So, but the main one are those the biggest company. And it's mainly the matter of money and number of people working on the companies on the subject. Uh, just a few words. When you use a quantum computer, the difficulty is that you cannot take your code and say, okay, I'm going to run this code and put it on the quantum computer. It will not work like that. So in order to use a quantum computer, you have to have an algorithm which use quantum weirdness. And the discovering of these quantum algorithms, it's a quite difficult task. And I put this slide to show that um, since the beginning of quantum computing, we have not discovered so much quantum algorithms. And that means that the somehow switching from classical thinking to quantum thinking is very hard. And that's certainly due because we don't understand really quantum mechanics and how it works. So most of the time, the discovering of quantum algorithm is not in the way of addressing a problem and designing an algorithm to solve this problem. Or is oftenly the other way around. That means that we discover something interesting quantum mechanically, and afterwards we fit a problem to it. And okay, a couple of domain on which quantum computing will play certainly a role. In research, you have all the domain of material science, CFD, computational fluid dynamics, drug discovery with quantum annulus. Finding the zero of a function is very similar to finding the molecular geometry. Batteries, etc. High energy physics also will be quantum computing will be very attractive for this field. You have also historically quantum computing was has a lot of interest in cryptography. And all the financial area were very interesting in finding ways to secure transactions and things like that. So they are very active also in the domain. All the domain of logistic also, because there are a lot of quantum computing is quite good when you have high combinatoric problems, so they can address this kind of things. And the defense area always looks at new technologies to improve the way to make war. And finally, I found a couple of articles. So if you Google a little bit quantum computing with Google Scholars, you'll find a lot of papers. So I found some papers in chemistry and in physics, mathematics, etc. So there are a lot of domain where people are putting times uh, to to struggle with quantum computing and to see how it can improve their research. So I'll stop here, and if you have any question.
Thank you, Frederic, for the presentation. Any question on the room? Yes, Suleiman?
Thank you very much for the presentation. I would love to ask if we could get the presentation
Yeah.
so we can have or I can review it and try to understand it in details. Thank you very much.
Yeah,
You're
you
welcome.
get the presentations, but also we have recorded the 3 presentations and they will be